Hello again. This is your friendly neighborhood math teacher here to continue to talk to you about calculus concepts. And today, well, it's still the same day as when I recorded the last video. So I could say today because it's true, but it's not like things have changed. I'm wearing the same clothes. So during the pandemic, I think a lot of people are wearing the same clothes all the time. We're going to go through a couple of examples from the homework. We're going to go through some definitions and try to get people more comfortable with this idea of derivatives. So first, let's give some definitions because there's nothing that gets us going like definitions. So we already talked about average rate of change in the last video. The average rate of change over an interval from a to b of function f would be the change in y over the change in x. That's f of b minus f of a over b minus a. If this sounds familiar to you, it should. This is just the rise over the run, which is just the slope. The average rate of change is just the slope. So when you see average rate of change, they're really just asking for the average slope of the line. That doesn't mean that it has to be the exact slope. So you can have a curve that looks like this, and I want the average rate of change from this point to this point. I just find the slope of this line, which is going to be f of b minus f of a, that's my change in y, over b minus a. That's all I have to do for finding average rate of change. Now, finding the instantaneous rate of change is a little bit more complicated, and that's where we get into these two guys right here, or gals. The derivative of a function is used to find the instantaneous rate of change. So, if we say that we want to find the derivative of the function f at x equals a, this is being marked as this thing. There's an f with an apostrophe of a. This is read as f prime of a. That's how we read this statement. So when we want to find the derivative of a function f at a, we say we're trying to find f prime of a. And in order to do this, we're going to take the limit as x and a get closer and closer and closer to one another. Yes, or in our last video, we did this by finding out what happened as values got closer and closer and closer to 4. We used 4.1 and 4, then 4.01 and 4, and 4.001 and 4 would have gotten even closer to 8. And we could have done that and gotten infinitely close. And that's what this idea of a limit is. We're trying to take the limit as x and a get closer and closer and closer to each other, essentially as 4.1 and 4 get closer and closer and closer to each other. And then we'll take f of x minus f of a over x minus a. This gives us the slope of the tangent line. So when we talk about a tangent line, which as I said in the last video is a concept that comes up a ton in calculus, the slope of the tangent line is just the derivative of the function. Now, this is not the only way that you'll see a derivative written. Another way that you'll see it written is as this, which is a little bit easier for calculation. This will look confusing to a lot of people at first. It says f prime of a is equal to the limit as h approaches 0 of f of a plus h minus f of a over h. Now, I'm going to do a little writing over here. Think about what was happening with our 4.1 and our 4. If we had h equaling 0.1, then we had f of a plus h, that was 4 plus 0.1 minus just f of a, which would be f of 4, divided by, now this is essentially my x value and this is my y value. So I would take 4 plus 0.1 minus 4. This 4 plus 0.1 is this bit and this 4 is this bit. Well, what's left over? Just the 0.1. Well, that is h, and that's where this is coming from. If instead I had made h equal 0.01, then I would have had f of 4.01, that's 4 plus 0.01, minus f of 4, divided by 4 plus 0.01 minus 4, which would give me f of 4.01 minus f of 4 divided by 0.01. Once again, it's this thing. And I'm trying to do this as h gets closer and closer and closer to 0. And if I do that, it's going to give me a derivative. So let's actually do a problem from your homework. And I'm going to do problem number 25. It asks you to find f prime of negative 2, given that f of x equals 3x squared plus 2. And they actually say to find the derivative at the value negative 2, but that would be the same as this statement. So we're going to do this using this thing up here. And this is going to look a little bit crazy for people. So what this means that we're going to do, I'm actually not going to deal with this negative 2 at all to start off with. I'm going to take this thing and I'm going to find the derivative of this thing. I'm going to use this, or find this using the difference quotient. And that's what this thing right here is called. This is called the difference quotient, because it's a quotient of differences. It's f of a plus h minus f of a, and then it's a plus h minus a, which leaves you just with h. This is just simplified. So I'm going to do that with this thing. I would need to find f of x plus h minus f of x divided by x plus h minus x. This is the difference quotient. It is a quotient of differences. And this is my function. So think about what would happen if I plugged x plus h into this thing. I would get 3 multiplied by x plus h squared minus, plus 2. Forgot about the plus 2. That's just taking x plus h and plugging it into this function. Minus f of x is just this thing. So I'm going to subtract 3x squared plus 2. And I'm going to divide that by x plus h minus x. And I'm taking this limit as h approaches 0. Because remember, my goal is to make this h as tiny as possible. I was going from 0.1 to 0.01 to 0.001. So I have x plus h minus x. And I'm going to write this whole thing out at first. Now, let's see what happens if I multiply all this out. I would have to use my exponent before I multiply by 3. So I would get 3 multiplied by x squared plus 2xh plus h squared. That's what happens if I distribute this all out. Plus 2 minus 3x squared minus 2 all over h, which gives me 3x squared plus 6xh plus 3h squared plus 2 minus 3x squared minus 2 all over h. Now again, these are all the limits as h approaches 0. The limit as h approaches 0. We're trying to find this thing as h gets closer and closer and closer to 0. Now I can't just plug 0 in right now, because if I plug 0 in right now, I'd end up dividing by 0, which I can't do. No dividing by 0 is allowed. So instead we're going to simplify. Well, I have a positive 3x squared here, and I have a negative 3x squared here. Those will cancel. A positive 2 here and a negative 2 here. Those will cancel also. And notice that the things that are left have h's in them. And this will always be the case when you use the difference quotient. When you distribute everything out, if you are left with things that don't have h's in them after you cancel, you've done it wrong. Because what we're going to do is we're going to factor an h out of these two remaining terms. So I'll have h multiplied by 6x plus 3h over h. And we're taking the limit as h approaches 0. Well, now I can get rid of the h. Well, now I just have 6x plus 3h. And if I'm taking the limit as h approaches 0, I want to know what this becomes as h gets closer and closer to 0. Well, as h gets closer and closer to 0, what's 3h going to get closer and closer to? Also 0, which means that what I'm left with is just 6x. 6x is my difference quotient. It is my derivative. This is the derivative. Yay! But I wanted the derivative at negative 2. Well, you just plug in negative 2. And so my derivative at negative 2 is going to be equal to negative 12. And negative 12 is going to be my answer. Now, this can be really, really intimidating to people. You guys haven't seen anything like this before, and I'm trying to teach it to you via a phone in a little video lesson. And maybe some of you will get it and maybe some of you won't get it. It's okay either way. You'll be fine. If you are taking calculus next year, I want you to remember, we're going to spend about a trimester working on finding derivatives. There are lots of different things we can do to make finding derivatives easier, and you will learn about those next year. But right now, I'm just trying to give you the basics of where this thing comes from. A derivative at its core is just a slope. A derivative specifically is an instantaneous slope. It's the slope at one little tiny point. And we find that slope at one little tiny point by taking 2 points and bringing them so close together that they're essentially the same point. We take the limit as that gap, that's h, gets closer and closer and closer to 0. And that idea is the idea of a derivative. And if you can understand that, then you understand half of calculus, well, a third of calculus at its core. We will work with this a lot more. Please do not get frightened off. If this seems like a lot, it will be all right. And I will be posting more videos to try to help people out with how things work. I hope you all are doing great, and I look forward to talking to you again soon. Be well, everyone, and keep on taking those derivatives. Bye.